And normally at an end of an AS paper, there is some sort of modelling question. So this is one on population modelling. So the population P in thousands, let's note that carefully, is in thousands, of a species is decaying and is modelled by P is equal to AE to the minus KT plus C, where T is the time in years and K is a positive constant. The initial population is 8,000, show that A plus C is equal to 8. If the population ultimately decays to 3,000, write down the value of C and hence determine the value of A. After 2 years, it's known that the population decreases to 5,000. Show that the value of K is 0.458, correct to 3 significant figures. Use your model to find out what the population is after 4 years and find the rate of change of population when T is equal to 4. Right, so our model is P is equal to AE to the minus KT plus C. When T is equal to 0, P is 8. We'll substitute that in. So we get 8 is equal to AE to the minus K times 0 plus C. We'll note that E to the 0 is actually equal to 1, so we'll get that 8 is equal to A plus C as required. We know as T goes to infinity, P is equal to A over E to the KT plus C. E to the minus KT becomes that, using the rules of indices. And therefore, here we're going to get A over a very, very large number, which we'll count as 0. So P will tend towards C. And we're told that it will tend towards 3,000. But remember, we're working in thousands, so therefore C is 3. We'll substitute that 3 into here. So we get 8 is equal to A plus 3. And therefore A will be equal to 5. So our model now is P is equal to 5e to the minus KT plus 3. So we've got C is 3, A is 5. Right, it is known, after 2 years, it's known that the population decreases to 5,000. So we've got P is equal to 5e to the minus KT plus 3. So at 5, substituting in, we get 5. P is 5. Remember, we're working in thousands, so we get 5e to the minus 2k. Minus 3 from both sides, we get that 2 is equal to 5e to the minus 2k. And we get e to the minus 2k is 2/5. Right, we know from our rules of logarithms that if we've got a to the c is equal to b, it implies that c is log to the base a of b. So the c is minus 2k, and log to the base e is written as ln of 2/5, and therefore dividing by minus a half, multiplying by minus a half, we get that k is minus 1 over 2 ln of 2/5, which will give me that k is equal to 0.4581, which is 0.45823 significant figures. So P is now equal to 5e to the minus 0.458t plus 3. When P is when t is 4, we get P of 4 is 5e to the minus 0.458 times 4 plus 3, which will give me 3.800. But remember that we want this in thousands, so it will be population will be 3,800. For the rate of change, we need to know that ddt of e times the constant of t means bring down the constant in front and then write down the same thing again. So when we differentiate this, we're going to bring down minus 0.458 times 5 and write down the same thing again. When you differentiate 3, you get nothing. Minus 0.458 times 5 gives you minus 2.29. And then when t is equal to 4, we'll substitute in. We get minus 2.29 e to the minus 0.458 times 4, which will give me minus 0.36666. And therefore the population is decreasing, minus, because it's decreasing, by 367 per year. If we look at this on the graph, here's the model of our population decrease of our function. Here we have when t is equal to 4, we can see the rate of change is minus 0.366. That's the gradient of that blue tangent. And here we have a horizontal asymptote at p is equal to 3, which is the limiting factor of our model. Okay, so this has been a video about population decay using an exponential function. I hope you've understood. In the note of this video, you'll find a link to my website, where you'll find thousands of videos to support you with A-level maths, and maybe you could consider subscribing to my channel. Thank you very much for watching.